Look up at the night sky. For thousands of years, we have seen it as a distant, unreachable canvas of stars, a beautiful but silent mystery. Yet right now, in this very moment, that silence is being broken. Our presence is no longer confined to a single planet. It is expanding, carried on the wings of incredible machines we have built with our own hands. We are living in a new golden age of space exploration, a time unlike any other in human history, and the missions currently underway are not just scientific endeavors. They are the first steps into a future we once only dreamed of in stories. What if the key to humanity's future, to our survival, our understanding, and our place in the cosmos, is already hurtling through the void, a collection of daring projects silently working to reshape reality itself? This video is a journey to meet those pioneers. We are going to explore 25 groundbreaking space missions, each one a testament to human ingenuity and boundless curiosity. These are not concepts on a drawing board. They are active, ongoing quests that have the potential to revolutionize everything. Imagine missions that could definitively answer the age-old question, are we alone? By finding biosignatures on distant worlds, consider telescopes so powerful they can peer back to the dawn of time, and spacecraft designed to defend our planet from catastrophic asteroid impact. We will witness the beginnings of interplanetary civilization, with projects laying the groundwork for sustainable life on Mars and perhaps even among the moons of the outer solar system. This is about more than just discovery. It is about our evolution as a spacefaring species. Every mission on this list carries a piece of that grand ambition. They represent a collective turning point, a moment where we move from simply observing the cosmos to actively engaging with it, learning from it, and preparing to become a part of it. The sense of wonder you feel is real because the achievements we are about to cover are truly extraordinary. They promise to unlock secrets about the universe's most profound mysteries, from the nature of dark energy to the possibility of life in the icy oceans of Europa. So, let's embark on this voyage together to discover the 25 missions that could change everything we know and everything we are. And we begin our journey with a mission that has already fundamentally rewritten our cosmic address. The James Webb Space Telescope is not merely an upgrade from its predecessor, Hubble. It is a completely different kind of eye on the universe. While Hubble showed us the cosmos in stunning visible light, Webb was designed to see in infrared light, a wavelength invisible to our eyes but rich with information. This is the key to its revolutionary power. Because the universe is expanding, the light from the very first stars and galaxies has been stretched as it travels across the vastness of space, shifting from visible light into the infrared part of the spectrum. By detecting this faint, ancient glow, Webb acts as a time machine, allowing us to witness events that occurred over 13.5 billion years ago, a mere heartbeat after the Big Bang itself. But its vision extends far beyond the dawn of time. One of its most profound tasks is to study the atmospheres of planets orbiting other stars, known as exoplanets. When one of these distant worlds passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Webb's exquisite instruments can analyze this filtered light, breaking it down into a spectrum that reveals the chemical fingerprints of the gases present. Scientists are hunting for specific combinations of gases like oxygen and methane that could be potential biosignatures, signs that might be produced by living processes. It's a delicate and complex search, but Webb has the precision to make it possible, bringing us closer than ever to answering the question of whether we are alone. The telescope's early observations have already delivered stunning surprises that challenge our textbooks. For instance, it has discovered galaxies in the very early universe that are far more massive and mature than anyone predicted. According to previous models, there simply shouldn't have been enough time for such well-structured galaxies to form so quickly after the Big Bang. This forces astrophysicists to reconsider the very timeline of cosmic evolution. Every new image from Webb is not just a pretty picture, it is a data-rich puzzle piece that is reshaping our understanding of how stars ignite, how galaxies assemble, and how the building blocks of life might be distributed throughout the cosmos. This mission is more than a telescope, it is our generation's portal to the deepest secrets of the universe. While the James Webb Space Telescope allows us to witness the universe's deepest past, another set of missions is firmly focused on securing humanity's future, beginning with our closest celestial neighbor. The Artemis Program represents a fundamental shift in our approach to space exploration. This is not a brief flag-planting exercise like the Apollo missions of the 1960s and 70s. Artemis is about building a permanent foothold. NASA's vision is clear: to establish a sustainable human presence on the Moon, creating a proving ground for the technologies and operations needed for the next giant leap: human missions to Mars. It's a multi-stage endeavor that will transform the Moon from a distant destination into a vibrant hub of human activity. The architecture of Artemis is built on a foundation of collaboration and reusability, centered around two key components. The first is the Lunar Gateway, a small space station that will orbit the Moon. Think of the Gateway not as a final destination, but as a sophisticated outpost or a celestial port of call. From this vantage point, astronauts can remotely operate rovers on the lunar surface, conduct scientific experiments in a deep space environment, and prepare for their descent to the Moon. The Gateway is crucial because it allows us to learn how to live and work far from Earth's protective magnetic field, dealing with the challenges of deep space radiation and isolation in a controlled way before committing to the much longer journey to Mars. The second component is the Artemis Base Camp, the envisioned sustainable habitat on the lunar surface itself, likely near the South Pole. This region is of immense scientific and practical interest because it contains areas of near-permanent sunlight for solar power generation and shadowed craters that may harbor water ice. Access to water is the key to sustainability. It can be split into oxygen for breathing and hydrogen for rocket fuel, effectively turning the Moon into a cosmic gas station. This base camp would support crews for weeks or even months at a time, enabling profound geological exploration and the development of technologies like using lunar soil, called regolith, for 3D printing structures, shielding astronauts from radiation. This entire program serves as an indispensable dress rehearsal for Mars. The Moon is only a 3-day journey away, allowing for relatively quick assistance if problems arise. Mars, by comparison, is a multi-month voyage each way with no possibility of a rapid return. By learning to construct habitats, generate resources, and operate reliably on the Moon, we are developing the operational handbook for deep space. Every problem solved and every lesson learned on the lunar surface directly reduces the risk and increases the chance of success for the first human footsteps on the red planet. Artemis is therefore much more than a return to the Moon. It is the foundational chapter in the story of humanity becoming a multi-planet species. Now, let's turn from the Moon's promising future to a current robotic endeavor on Mars that is arguably one of the most complex scientific projects ever conceived. The Mars Sample Return mission is not a single spacecraft launch. It is an intricate multi-stage ballet involving an international fleet of robots working in perfect harmony across tens of millions of miles. The ultimate goal is as audacious as it is simple: to bring pristine pieces of another planet back to Earth for the very first time. Why is this so important? While our rovers are incredible mobile laboratories, they are severely limited by their size and power. The most sophisticated instruments we have for detecting subtle signs of past life are the size of a room and require meticulous preparation that simply cannot be replicated on a rover. Bringing Martian samples to Earth allows us to apply the full might of our global scientific community to these precious rocks, using equipment of unparalleled sensitivity. The first act of this cosmic drama is already playing out on the Martian surface, starring NASA Perseverance rover. Since its landing in Jezero crater in 2021, Perseverance has been acting as a highly skilled field geologist. Its mission is not just to explore, but to carefully select and collect the most promising samples. Jezero crater was chosen because it was once a river delta, a place where water once flowed into a large lake. On Earth, river deltas are exceptional at preserving the evidence of ancient life, and scientists hope the same is true for Mars. Perseverance is equipped with a sophisticated sampling system that drills core samples from interesting rocks and seals them inside ultra-clean titanium tubes. It doesn't just drop them randomly, it methodically creates a sample cache depot, a carefully mapped collection of these tubes on the surface, creating a geological treasure chest for a future mission to retrieve. The next phase of this ambitious plan involves a relay race of spacecraft. The second critical player will be the Sample Retrieval Lander, a mission currently in development. This lander will carry two new elements to the surface of Mars. The first is a small fetch rover provided by the European Space Agency, which will be deployed to swiftly navigate to Perseverance's cache depot, pick up the sample tubes and bring them back to the lander. The second is the Mars Ascent Vehicle, a small but powerful rocket that will be the first object ever to launch from the surface of another planet. Once the samples are loaded into a special container atop this rocket, it will blast off from Mars, carrying its priceless cargo into orbit. But the journey is only half over. Waiting in Martian orbit will be the third major component, the Earth Return Orbiter, another significant contribution from the European Space Agency. This spacecraft must locate the sample container, rendezvous with it in orbit, and safely capture it. Once secured inside a highly secure and biocontained system designed to prevent any potential forward contamination of Earth, the orbiter will begin its long voyage home. Upon approaching Earth, it will release the Earth Entry Vehicle, a capsule designed to withstand the fiery heat of atmospheric re-entry, ultimately parachuting the Martian samples safely to a landing site, likely in a remote desert area. The scientific payoff of successfully completing this intricate chain of events is almost incalculable. In laboratories on Earth, scientists will be able to analyze the mineral composition, look for organic molecules, and search for morphological fossils or other biosignatures with a level of detail that is impossible remotely. They can date the rocks with extreme precision, telling us not just if life could have existed on Mars, but if it actually did. The answers locked within these samples could tell us whether life is a cosmic imperative, emerging wherever conditions are right, or if Earth is a singular miracle. This mission is more than a technical feat. It is a direct quest for one of the most profound discoveries imaginable. But to truly grasp the variety of worlds where life might arise, we must journey far beyond the inner solar system, to a place so alien it challenges our very definition of a habitable environment. Orbiting Saturn is a moon unlike any other, a world shrouded in a thick, golden haze with rivers and lakes not of water but of liquid methane. This is Titan, and NASA Dragonfly Mission is a daring, almost science-fictional endeavor designed to explore its secrets. Imagine a robotic explorer, not on wheels but with rotors, flying through the dense, nitrogen-rich atmosphere of this distant moon from one site of interest to another. Dragonfly is essentially a large, nuclear-powered drone, an 8-rotor rotorcraft that will use Titan's low gravity and thick atmosphere to its advantage, making flight far more efficient than it is on Earth. This mission is not just about geological exploration. It is a profound quest to understand the chemistry of life itself. Titan is often described as a frozen analog of early Earth, a natural laboratory where we can observe the kinds of chemical reactions that may have occurred on our own planet billions of years ago, before life ever emerged. On Earth, that history has been erased by billions of years of geological activity and biology itself. But on Titan, these probiotic processes are likely frozen in time, preserved in its deep freeze conditions. The complex organic molecules that rain down from the atmosphere and collect on the surface are the very building blocks that, under the right conditions, could lead to life. Dragonfly's core mission is to investigate this probiotic chemistry, to see how far along this path Titan has progressed without actually crossing the threshold into biology. The rotorcraft will land initially in the Shangri-La Dune Fields, an area similar to the linear dunes found in Namibia on Earth. But from there, its true capability shines. It will take flight, traveling tens of kilometers at a time to visit dozens of different locations over a planned mission of nearly 3 Earth years. This mobility is revolutionary. It allows Dragonfly to sample a wide variety of environments, from the organic-rich dunes to the floor of the Selk impact crater, where evidence of past liquid water may exist. The lander is equipped with a full suite of instruments to drill into the surface and analyze the composition of these materials, searching for complex organic molecules and even isotopic signatures that could hint at water-based or hydrocarbon-based life processes. By studying this world of methane cycles and organic chemistry, Dragonfly will answer fundamental questions about the habitability of icy moons throughout the galaxy. If life can start with a different solvent, like liquid methane instead of water, then the number of potentially habitable worlds in the universe expands dramatically. This mission will teach us about the resilience and diversity of life's ingredients, pushing the boundaries of our understanding. Dragonfly is not just going to another moon, it is embarking on a voyage to a different version of planetary evolution, one that could reveal entirely new rules for how a world can become alive. While Titan presents a world of exotic chemistry, another moon in our solar system offers a more familiar and perhaps even more compelling promise for life, a vast global ocean of salty water. Jupiter's moon Europa, with its cracked and icy surface, is the target of one of NASA's most anticipated missions, the Europa Clipper. This isn't a lander, it's a sophisticated orbital scout designed to answer the most critical question about this enigmatic world: could its hidden ocean support life? To do this, Clipper will embark not on a single orbit around Europa, but on a daring campaign of over 40 close flybys, swooping down as low as 25 kilometers above the surface. This unique trajectory is a masterstroke of orbital mechanics, allowing the spacecraft to map nearly the entire moon while minimizing its exposure to Jupiter's intense and damaging radiation belts. The heart of the mission lies in its powerful suite of 9 instruments, each designed to probe different secrets of the moon. A radar system will send signals deep into the ice, mapping the thickness of the icy shell and searching for pockets of liquid water closer to the surface, much like scientists use radar to map subglacial lakes in Antarctica. A magnetometer will measure the subtle changes in Jupiter's powerful magnetic field as it interacts with Europa's interior. The way this field is induced provides the strongest evidence we have for that global ocean, suggesting it's salty and conductive, sloshing beneath the ice. Thermal instruments will scan the surface for warm spots, areas where heat from the moon's interior might be melting the ice from below, potentially creating environments where life could thrive. One of the most exciting possibilities, however, involves catching a direct sample of the ocean without ever touching down. Hubble Space Telescope observations have provided tantalizing hints that Europa occasionally spews enormous plumes of water vapor into space through cracks in its icy crust. If these plumes are real and active, Europa Clipper could fly right through them. Its mass spectrometer would be able to taste the particles, analyzing their composition for complex organic molecules, salts, and other chemicals that would tell us about the ocean's habitability. Finding evidence of hydrothermal vents on the ocean floor, similar to those on Earth that support vast ecosystems without any sunlight, would be a revolutionary discovery. It would suggest that Europa's ocean has not only water but also a source of chemical energy that could power biological processes. Understanding Europa is about more than just one moon. It's a key to understanding a whole class of worlds. Ocean worlds like Europa, along with Saturn's Enceladus and possibly others, may be the most common habitable environments in our galaxy, far outnumbering Earth-like planets. The Europa Clipper mission is our first dedicated step toward exploring this new paradigm for life. By confirming the ocean's existence, characterizing its properties, and searching for those telltale signs of chemical energy, Clipper will lay the groundwork for the next logical step, a lander that could drill or melt its way through the ice to directly explore the ocean itself. This mission is a reconnaissance of a potential second genesis of life in our own cosmic backyard. Turning from the targeted exploration of ocean worlds, we shift our gaze back toward the grand architecture of the cosmos itself, where the greatest mysteries are not found on any single world but are woven into the very fabric of space and time. To tackle these profound puzzles, we need a new kind of observatory, one that doesn't just look deeply at a small patch of sky, but instead captures the entire heavens with an almost cinematic speed and clarity. This is the revolutionary purpose of the Vera C. Rubin Observatory, a facility perched on a mountaintop in Chile that is poised to transform astronomy from a series of snapshots into a dynamic, moving picture of the universe. Its mission is centered around the Legacy Survey of Space and Time, or LSST, an ambitious 10-year project that will scan the entire available sky every few nights, creating the largest astronomical movie ever made. The sheer scale of the data this observatory will produce is almost beyond comprehension. Each night, its immense 3.2 gigapixel camera, the largest digital camera ever built for astronomy, will capture over 800 panoramic images of the sky. Over a decade, this relentless observation will generate a catalog of over 20 billion galaxies and a similar number of stars, effectively mapping the visible universe in unprecedented detail. But the true power of the LSST lies not just in the depth of this map, but in its repetition. By photographing the same areas of sky again and again, the survey will detect anything that changes, moves, or flashes into existence. This will allow scientists to monitor millions of transient events in near real time, from stellar explosions in distant galaxies to the subtle motions of asteroids within our own solar system. One of the most significant contributions of the Vera C. Rubin Observatory will be to shed light on the invisible components that dominate our cosmos, dark matter and dark energy. We know that these enigmatic forces make up 95% of the universe, yet we cannot see them directly. The observatory will study dark matter by observing its gravitational influence on visible matter. It will use a technique called weak gravitational lensing, where the light from distant galaxies is slightly distorted as it passes through massive clumps of dark matter on its journey to Earth. By meticulously measuring the subtle warping of millions of galaxy shapes, astronomers can create a three-dimensional map of the dark matter scaffolding that underpins the cosmos, revealing its distribution and how it has evolved over billions of years. At the same time, the survey will provide our most precise measurements yet of dark energy, the mysterious force responsible for the accelerating expansion of the universe. By counting galaxy clusters across vast distances and studying the large-scale structure of the universe at different epochs in cosmic history, the LSST will trace how the rate of expansion has changed over time. This data is crucial for testing whether dark energy is a constant force, as Einstein's cosmological constant suggests, or whether its strength has varied, which would point toward entirely new and undiscovered physics. The observatory's comprehensive data set will essentially allow us to chart the history of the universe's expansion with a precision never before possible, putting our most fundamental theories of cosmology to the ultimate test. Beyond these deep cosmological questions, the Vera C. Rubin Observatory will act as a premier sentinel for our own planetary neighborhood. Its rapid-fire scanning of the sky makes it exceptionally powerful for discovering near-Earth objects, asteroids, and comets whose paths bring them close to our planet. It is estimated that the LSST will discover hundreds of thousands of new asteroids, dramatically increasing our catalog of potentially hazardous objects and providing decades of advance warning should any be found on a collision course with Earth. This proactive mapping is our first and best line of defense, turning what was once a game of cosmic chance into a manageable risk that we can monitor and, if necessary, plan to deflect. The observatory's ability to catch brief, fleeting events will also open a new window on the most violent and energetic processes in the universe. It will detect thousands of supernovae, the cataclysmic explosions of stars every night, providing a vast statistical sample to understand the end stages of stellar evolution. It will spot the brilliant flashes of gamma-ray bursts and the collisions of dense stellar remnants like neutron stars, events that ripple the fabric of space-time itself. By alerting other telescopes around the world within seconds of detecting such a transient event, the Vera-C, Rubin Observatory will act as the nervous system for a global network of observatories, enabling rapid follow-up observations that can catch the aftermath of these cosmic explosions in wavelengths from radio waves to X-rays. This facility is not just a telescope, it is a gateway to a new era of time-domain astronomy, where the changing, dynamic universe becomes the primary focus of our exploration. While the James Webb Space Telescope acts as a powerful cosmic microscope, peering into the deepest recesses of space and time, the next great observatory in NASA's lineup is designed to be a wide-angle lens for the universe. The Nancy Grace Roman Space Telescope, named for NASA's first chief astronomer who is often called the Mother of Hubble, is built for a different kind of discovery. Its mission is to survey vast stretches of the cosmos with a staggering speed and breadth, addressing questions that require a panoramic view rather than an intensely focused gaze. Where Webb might spend days observing a single galaxy cluster in exquisite detail, Roman will capture thousands of galaxies in a single snapshot, fundamentally changing the scale at which we can conduct our cosmic censuses and map the structure of everything that exists. The key to this capability is Roman's immense field of view. Its primary instrument, the Wide Field Instrument, will have a field of view that is about 100 times larger than the Hubble Space Telescope's infrared camera. To put that into perspective, a single Roman image covering the area of the sky held by a full moon would require hundreds of separate Hubble images to stitch together. This wide field strategy is perfectly tailored for one of its primary objectives, investigating the mystery of dark energy. By measuring the positions and distances of millions of galaxies across cosmic history, Roman will trace the influence of dark energy on the expansion of the universe with unparalleled precision. It will use techniques like measuring the distortion of galaxy shapes due to weak gravitational lensing and cataloging the clustering of galaxies over immense volumes of space. This will allow scientists to determine whether dark energy has remained constant over time or if its properties have evolved, which would have profound implications for the ultimate fate of the cosmos. Beyond cosmology, this expansive vision makes Roman an exceptional tool for finding and studying worlds beyond our solar system. It will conduct a groundbreaking microlensing survey to discover exoplanets that are incredibly difficult to find with other methods. Microlensing occurs when the gravity of a foreground star and any planets orbiting it acts like a magnifying glass, briefly amplifying the light from a more distant background star. This technique is particularly sensitive to finding planets at great distances from their host stars, including rogue planets floating freely in interstellar space unbound to any sun. Roman's survey is expected to discover thousands of these distant worlds, including many that are Earth mass, giving us our first true statistical understanding of the population of planets throughout the galaxy. Perhaps its most visually stunning capability, however, lies in its technology for direct observation. Roman will be equipped with a sophisticated coronagraph, an instrument designed to block the overwhelming glare of a host star, allowing the much fainter light of orbiting planets to be seen directly. While other telescopes have directly imaged a handful of large, young, hot planets far from their stars, Roman's coronagraph is a technological demonstrator that aims to be orders of magnitude more powerful. It will use complex masks and deformable mirrors to cancel out starlight with a precision never before achieved in space. The goal is to directly image and take spectra of giant planets similar to Jupiter and Neptune in other star systems, but more importantly, it will pave the way for future telescopes to do the same for Earth-like worlds. By analyzing the light from these directly imaged planets, scientists will be able to discern the chemical composition of their atmospheres. They will look for the signatures of water vapor, methane, carbon dioxide, and even potential biosignatures like oxygen. This is a critical stepping stone in the grand search for life. While Webb can analyze the atmospheres of planets that transit their stars, that method is limited to systems aligned edge-on from our viewpoint. Roman's coronagraph will allow us to study planets in a variety of orbital configurations, dramatically expanding our search space. Together, the Nancy Grace Roman Space Telescope and the James Webb Space Telescope represent a powerful partnership, one mapping the universe in breathtaking detail, and the other conducting a sweeping survey of its grandest structures and most promising planets, working in tandem to answer humanity's biggest questions. Moving from the panoramic surveys of the Roman telescope, we narrow our focus to a mission with a very specific and profound goal: to find another Earth. While we have discovered thousands of exoplanets, the vast majority orbit small, cool, and often volatile stars known as red dwarfs. Planets in the habitable zones of these stars are tidally locked, with one side in perpetual daylight and the other in endless night, and they are frequently bombarded by powerful stellar flares. The question remains, could a planet orbiting a star like our own Sun, a stable G-type star, offer a more familiar recipe for life? This is the driving purpose behind the European Space Agency's Pluto mission, a powerhouse observatory designed to hunt for worlds that truly resemble our own. The name Pluto, which stands for planetary transits and oscillations of stars, reveals the twofold nature of its scientific pursuit. Its primary tool is the transit method, a technique we are now familiar with, where a planet passing in front of its host star causes a tiny, predictable dip in the star's brightness. But Pluto is engineered for unprecedented precision and endurance in this hunt. It will not simply glance at stars, it will stare intently at two large areas of the sky for up to 2 years each, continuously monitoring several 100,000 of the brightest sun-like stars. This long-term, unwavering gaze is crucial because it allows the spacecraft to detect not just one transit, but the repeated, rhythmic dimming that confirms an orbital period. For a planet in the habitable zone of a sun-like star, that period would be about 1 Earth year, meaning Pluto must watch the same star for multiple years to be certain of its discovery. What truly sets Pluto apart, however, is its unique approach to instrumentation. Instead of one large telescope, it uses an array of 26 individual small cameras. This clever design serves two critical functions. First, it provides an exceptionally wide field of view, allowing it to monitor a vast number of stars simultaneously. Second, and more importantly, the cameras operate in two different modes. Most of them are fast cameras, taking measurements every 25 seconds, which is ideal for catching the brief dip of a planetary transit. But a few are slow cameras, gathering light over a longer period to observe very bright stars with extreme sensitivity. This dual approach ensures that Pluto can capture the faint signal of an Earth-sized planet, while also gathering incredibly detailed data on the stars themselves. This leads to the second part of its mission, stellar oscillations. Stars are not silent, static orbs. They resonate like giant musical instruments, pulsating and vibrating due to the tumultuous nuclear reactions in their cores. These vibrations cause tiny, rhythmic changes in a star's brightness and temperature. Pluto's name is a complete description of its work. By observing the oscillations of stars, a field known as astroseismology, the mission can peer directly into a star's heart. Just as geologists use seismic waves from earthquakes to map the interior of our planet, astronomers will use these stellar oscillations to determine a star's mass, radius, and most importantly, its precise age. This is a game changer for exoplanet science. Knowing the exact age of a star, and therefore the planetary system it hosts, adds a crucial dimension to our search for life. A young, fiery star might be too active, with frequent flares that could strip away a planet's atmosphere. A very old star might have a planetary system that has settled into a stable but potentially lifeless state. Finding an Earth-sized planet in the habitable zone is one thing, but confirming that it orbits a mature, stable, sun-like star that is several billion years old, providing ample time for life to arise and evolve, is what makes a discovery truly Earth-like. Pluto will provide this context with a level of accuracy never before achieved, allowing us to distinguish which worlds are not just the right size and distance, but also have the right stellar conditions to be considered prime candidates for habitability. The legacy of Pluto will be a catalogue of planetary systems around stars like our Sun, characterized with an unparalleled depth of information. For the most promising candidates, we will know the planet's size, orbital period, and the detailed properties of its host star. This carefully vetted list will become the primary target list for the next generation of giant ground-based telescopes, like the Extremely Large Telescope and future space observatories. These powerful instruments will then attempt to analyze the atmospheres of these worlds, searching for the biosignatures that Pluto discoveries have highlighted as the most worthy of investigation. In this way, Pluto is not an endpoint. It is the essential census taker, the sophisticated filter that will guide our gaze to the handful of worlds out of thousands that hold the most promise for answering the ultimate question. Now let's shift from the light we can see to the ripples we can feel, exploring a mission that will sense the cosmos not with light but with gravity itself. For centuries, astronomy has been the study of light, from the visible spectrum to radio waves and X-rays. But a new window onto the universe was thrown open in 2015, when the ground-based LIGO Observatory made the first direct detection of gravitational waves, tiny ripples in the fabric of spacetime predicted by Einstein a century earlier. These waves are created by the most violent events in the cosmos, like the collision of black holes. But ground-based detectors like LIGO have a limitation. They are sensitive to a specific, high-frequency range of these cosmic ripples, missing a vast symphony of lower-frequency waves that simply cannot be detected on Earth due to seismic noise and the planet's own gravitational curvature. To listen to this deeper cosmic hum, we need to go to space. This is the extraordinary goal of the Laser Interferometer Space Antenna, or LISA. This is not a single telescope, but a fleet of 3 identical spacecraft flying in a perfect triangular formation, trailing behind Earth in its orbit around the Sun. The scale of this formation is almost impossible to visualize. Each side of the triangle will be 2.5 million kilometers long, about 6 times the distance from the Earth to the Moon. Flying millions of kilometers apart, these 3 spacecraft will create the most sensitive measuring device ever built. At the heart of each spacecraft is a pair of solid gold platinum cubes, each about the size of a small computer speaker, floating freely in a vacuum chamber, isolated from all external forces except one: gravity. These are their test masses. The principle of operation is one of breathtaking precision. As a gravitational wave passes through the solar system, it will ever so slightly warp the fabric of space, changing the distance between these spacecraft. LISA will continuously fire laser beams between each pair of satellites, measuring the distance between those floating test masses with an accuracy of a few picometers. A picometer is 1/1,000,000th of a meter, far smaller than an atom. The mission must detect a change in distance that is smaller than the width of a single DNA strand across a void of millions of kilometers. By monitoring the precise laser light travel time between all 3 points, LISA can not only detect the wave but also triangulate its source in the sky, telling us exactly where in the universe the cataclysm occurred. By operating in the quiet of space, LISA will open up the low-frequency gravitational wave spectrum, a band filled with the sounds of the universe's most massive and enduring events. Its primary targets will be the mergers of supermassive black holes. These monsters, weighing millions or even billions of times the mass of our Sun, lurk at the centers of galaxies. When galaxies collide, their central black holes eventually spiral together and merge, generating gravitational waves that are millions of times stronger and with much longer wavelengths than those from stellar mass black holes. LISA will be able to detect these colossal mergers happening anywhere in the observable universe, effectively allowing us to witness the growth of galactic cores throughout cosmic time. But the discoveries will go far beyond black hole collisions. LISA will be able to detect the gentle, continuous hum produced by the cosmic population of millions of binary white dwarf stars within our own Milky Way galaxy. It could spot the subtle signal of a small, Earth-mass planet orbiting a special type of dead star known as a white dwarf binary, revealing worlds in star systems we could never see with light. Perhaps most intriguingly, LISA might even detect echoes from the very earliest moments of the universe, a stochastic gravitational wave background that could carry information about the Big Bang itself, from a time before the universe became transparent to light. This mission will transform our sense of the cosmos from a silent movie into a rich, multi-sensory experience, allowing us to literally feel the vibrations of the universe and listen to the hidden stories of gravity. Our journey now takes us from the frigid ocean worlds and cosmic observatories to a place of ancient and terrifying wonder, a world that serves as a stark warning about the fragility of planetary environments. Venus, often called Earth's twin, is in reality our planet's evil twin. It is nearly the same size as Earth and formed from similar materials in the same neighborhood of the early solar system. Yet today, its surface is a crushing, scorching hellscape, with temperatures hot enough to melt lead and an atmosphere of corrosive sulfuric acid clouds with a pressure 90 times greater than Earth. How did these two sibling worlds end up on such radically different paths? This is one of the most pressing questions in planetary science, and NASA has 2 dedicated missions, DAVINCI+ and VERITS, designed to work in tandem to unravel this profound mystery. First, let's meet DAVINCI+, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. This mission is a true descent into the unknown. While orbiters have studied Venus from above, no spacecraft has entered the Venusian atmosphere to study its chemistry since the Soviet Venera and Vega probes in the 1980s, and none with the sophisticated instruments available today. DAVINCI+ is essentially a flying chemistry lab packed into a rugged, spherical probe designed to survive a 1-hour plunge through the planet's thick, hostile atmosphere. Its strategy is beautifully direct. It will dive right in, transmitting data as it falls, layer by layer, until it reaches the surface. The probe's descent is a carefully choreographed scientific investigation. As it falls, it will first sample the upper and middle cloud decks, analyzing the composition of those infamous sulfuric acid clouds and searching for unknown chemical constituents. A key focus will be on measuring noble gases like krypton and xenon, along with different isotopes of elements. These gases are inert. They do not react with other chemicals, so they act as ancient fossils, preserving a record of the conditions present when Venus first formed and the processes that shaped its early atmosphere. The precise ratios of these gases will tell us if Venus started with as much water as Earth, and if so, when and how it lost it all to a runaway greenhouse effect. The mission will also look for signs of active volcanism by detecting volcanic gases wafting up from below, and it will even capture the first high-resolution images of the planet's unique tesserae, highly deformed mountainous regions that may be analogous to Earth's continents as it approaches the surface. While DAVINCI+ acts as an atmospheric detective, its partner mission, VERITLS, will be the planet's geologist, creating a global map of Venus's surface with a clarity we have never before achieved. VERITLS, the Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy mission, will orbit the planet and peer through the obscuring clouds using a powerful radar system. Think of it as giving Venus a full-body CT scan. Its primary instrument will create topographic maps with a resolution far exceeding those from the 1990s Magellan mission, revealing the shape of volcanoes, lava flows, and tectonic features in exquisite detail. It will be like upgrading from a blurry black and white photograph to a high-definition, three-dimensional model. This detailed mapping will allow scientists to answer fundamental questions about Venus's geological activity. Is the planet still volcanically alive today? VERITLS will look for subtle changes in surface temperature that might indicate recent lava flows, as well as measure minute deformations in the crust that could signal magma moving underground or active tectonic shifts. By studying the types of rocks on the surface using a near-infrared spectrometer that can identify specific minerals, the mission will help us understand Venus's geological history. Did it ever have a system of plate tectonics like Earth's, which is crucial for recycling carbon and regulating climate? Or did it follow a different path with a stagnant lid of crust that led to a catastrophic buildup of heat and a global resurfacing event? Understanding this geological past is the key to unlocking the climate history that DAVINCI+ is investigating. Together, these two missions form a powerful, complementary team. VERITLS provides the big-picture context, the global landscape and its history, while DAVINCI+ provides the ground truth, measuring the actual chemistry of the atmosphere and surface rocks at a specific, scientifically critical location. The data from one will inform and enhance the discoveries of the other, creating a holistic picture of how Venus works as a system. By studying this planetary tragedy next door, we gain invaluable insights into the delicate balance that makes a world habitable. Venus stands as a constant reminder that a planet's fate is not sealed at birth. The missions DAVINCI+ and VERITLS are not just about understanding a distant, hostile world. They are about understanding the limits of our own and the conditions that allow a pale blue dot to flourish rather than burn. While long-term visions like Artemis focus on human presence, a more immediate and perhaps equally revolutionary transformation is happening just beneath the surface, driven not solely by government agencies but by a burgeoning wave of commercial innovation. This shift is embodied by NASA, a Commercial Lunar Payload Services Program, or CLPS. Think of CLPS not as a single mission, but as a new business model for space. Instead of NASA designing, building, and operating its own lunar landers, the agency acts as an anchor customer, purchasing delivery services from a variety of American companies. This approach is designed to catalyze a commercial lunar economy, where private industry develops the vehicles and the expertise to routinely transport cargo to the moon, dramatically lowering costs and accelerating the pace of exploration. The genius of this strategy is its competitive, lean approach. Multiple companies, from established aerospace firms to nimble startups, are developing their own unique lander designs. Some are small and focused on delivering a few dozen kilograms of payload, while others are larger, capable of carrying rovers and more substantial scientific instruments. This competition fosters innovation and drives down prices, creating a vibrant market where NASA can send its instruments more frequently and for a fraction of the traditional cost. These CLPS deliveries are the supply ships for the new lunar frontier, carrying everything from technology demonstrations and scientific experiments to the first critical infrastructure needed for a sustained human presence. The very first of these missions, while facing challenges, have already demonstrated the potential of this new pathway, proving that commercial entities can successfully reach the lunar surface. A primary objective for many early CLPS flights is a treasure hunt for one of the Moon's most valuable resources, water ice, as we discussed with Artemis, confirming the quantity, purity, and accessibility of water ice locked in the permanently shadowed craters at the lunar poles is a game-changer. Several upcoming CLPS missions are specifically designed as prospectors. They will carry advanced spectrometers and neutron spectrometers that can map the distribution of hydrogen, a key indicator of water, from orbit and directly on the surface. Some will even attempt to drill into the regolith, extract samples, and use onboard instruments to analyze the soil, testing methods for actually processing the ice into usable water, oxygen, and hydrogen fuel. This isn't just academic science, it's the foundational work for lunar in situ resource utilization, the practice of living off the land. The ability to create rocket fuel on the Moon would fundamentally alter the economics of deep space exploration. Think of the lunar poles as a potential cosmic gas station. Water ice can be split into liquid hydrogen and liquid oxygen, the very propellants used by many modern rockets. A spacecraft launching from Earth to Mars would need to carry all the fuel for its entire journey, a massive and expensive burden. But if it could launch with just enough fuel to reach the Moon, refuel at a lunar depot, and then depart for Mars, the mission becomes far more efficient and capable. This concept, known as cislunar infrastructure, turns the Moon into a strategic waypoint rather than just a destination. The data gathered by these commercial prospectors will determine the feasibility of this vision, guiding where we might build the first permanent refueling outposts. But a thriving lunar economy needs more than just resources. It requires reliable utilities, starting with a dedicated communication and navigation system. Imagine astronauts or rovers operating on the far side of the Moon, completely cut off from direct line of sight with Earth. Or consider the challenge of landing multiple vehicles in the same region without a precise GPS-like network to guide them. This is why plans are already underway to establish LunarNet, a proposed framework for lunar communications and navigation services. The initial architecture would likely involve a constellation of small satellites placed in special orbits around the Moon, providing constant coverage for most of the lunar surface. This network would function much like our terrestrial internet and GPS combined. It would allow for high-bandwidth communication, enabling the transmission of high-definition video from rovers and the streaming of vast amounts of scientific data back to Earth. Simultaneously, it would provide precise timing and location services, allowing landers to touch down with centimeter-level accuracy and enabling rovers to navigate autonomously across the treacherous lunar terrain. This infrastructure is not a luxury. It is a necessity for the coordinated, large-scale activity that a sustained lunar presence demands. It represents the shift from conducting individual, isolated missions to building an integrated operating system on another world. Together, the CLPS deliveries and the development of lunar utilities are laying the pragmatic, brick-by-brick foundation for the future that Artemis envisions, transforming the Moon from a silent companion in the sky into a busy hub of human enterprise. Imagine a world not of rock or ice, but of gleaming, solid metal. This is not science fiction. It is the reality of an asteroid named Psyche, the destination of one of NASA's most extraordinary voyages of discovery. While most asteroids are rocky or icy remnants from the solar system's formation, Psyche is something entirely different. Scientists believe it is the exposed nickel-iron core of a protoplanet, a building block of a planet that was violently stripped of its rocky mantle during the chaotic collisions of the early solar system. If this hypothesis is correct, then Psyche offers a once-in-a-lifetime opportunity, a chance to study a planetary core up close, something we can never do on Earth, as our own planet's core is buried thousands of kilometers beneath the crust, forever hidden by the mantle and crust. This mission is, in essence, a journey to the heart of a world that never was, providing a unique window into the secret interior of planets like our own. The scientific value of reaching this metallic world is immense. By carefully mapping its composition, structure, and magnetic field, the Psyche spacecraft will test fundamental theories about how the terrestrial planets Mercury, Venus, Earth, and Mars accreted from smaller bodies. We understand the basic process. Dust grains clumped together to form planetesimals, which then collided and merged to form protoplanets. But what happened during those colossal impacts? Did the metallic cores of these protoplanets merge completely, or did they shatter and mix? Measuring the exact proportions of elements like iron, nickel, and potentially rare metals like gold and platinum within Psyche will provide crucial clues. The asteroid's surface topography will also tell a story. Is it covered in the giant impact craters and metal spikes expected from a world that endured such cosmic violence, or does it show evidence of ancient magnetic activity frozen in time? Each piece of data will help us rewrite the chapter on planetary formation. To reach this distant relic, the Psyche spacecraft is equipped with a revolutionary propulsion system that marks a significant step forward in deep space travel: advanced solar electric propulsion. Unlike traditional chemical rockets that provide a short, powerful burst of thrust but carry immense weight in fuel, this system is a model of efficiency. It works by using large solar arrays to capture sunlight and convert it into electricity. That electricity is then used to power a highly efficient engine that ionizes xenon gas, a neutral propellant, turning it into a stream of charged particles or ions. These ions are then accelerated out of the engine by a powerful electric field, creating a gentle but continuous thrust. The glow of this ion beam is a faint bluish hue, a testament to its steady, relentless push. The key advantage of this technology is its incredible fuel economy. While the thrust is much weaker than a chemical rocket, often compared to the gentle pressure you feel holding a single sheet of paper in your hand, it can operate continuously for weeks, months, or even years. Over the long journey to the asteroid belt, this constant acceleration adds up, allowing the spacecraft to achieve very high speeds while consuming only a tiny fraction of the propellant a chemical rocket would require. This mission will serve as a crucial testbed for this technology, demonstrating its viability for future cargo missions or even crewed missions to distant destinations where efficient propulsion is essential for carrying the supplies needed for long-duration voyages. The quiet, steady hum of its engines represents the future of interplanetary travel, a method that prioritizes endurance over brute force. After a long journey spanning billions of kilometers, the spacecraft will enter orbit around Psyche in 2029, beginning an intensive 21-month investigation. It will use a suite of sophisticated instruments to unravel the asteroid's mysteries. A multispectral imager will capture high-resolution pictures of the surface, revealing its geological features in stunning detail. A gamma-ray and neutron spectrometer will peer beneath the surface, mapping the elemental composition to confirm if Psyche is indeed predominantly metal. And a magnetometer will search for any remnant of a magnetic field, a ghostly echo of the dynamo that may have once churned within this metallic core when it was molten, which would be the strongest evidence yet that this is a true planetary core. The data returned will not just be about one strange asteroid. It will be a foundational chapter in the story of our own planet's violent and dramatic birth, revealing the hidden heart of worlds. Leaving the metallic world of Psyche behind, our journey pushes further out into the solar system, toward a destination of staggering complexity and profound potential for life, the Jupiter system. While NASA Europa Clipper is focused intensely on a single moon, the European Space Agency's J-Jupiter Icy Moons Explorer, or JUICE, embarks on a broader grand tour. This ambitious mission is designed to conduct a comparative planetology study of 3 of Jupiter's largest moons, Ganymede, Callisto, and Europa, all of which are believed to harbor vast global oceans of liquid water beneath their icy crusts. By studying these 3 worlds together, JUICE aims to answer a fundamental question: what makes an icy moon habitable? It will explore not just the moons themselves, but how they interact with their king, the gas giant Jupiter, creating a dynamic system unlike any other we have studied. The mission's itinerary is a masterclass in orbital mechanics and scientific strategy. After a long cruise that includes gravity assists from Earth and Venus, JUICE will arrive at Jupiter in 2031. It won't go into orbit around Jupiter directly. Instead, it will use the planet's immense gravity to swing itself into a series of increasingly complex orbits, allowing it to perform 35 close flybys of the 3 moons over a 3-year period. This dance through the Jovian system will provide breathtaking opportunities. It will make 2 close passes by Europa, the most geologically active of the trio, to study its surface composition and search for those tantalizing plumes of water vapor. It will then conduct 12 flybys of the enigmatic, heavily cratered Callisto, a world that may represent a pristine relic from the earliest days of the solar system. Finally, the mission will culminate in a dramatic and historic maneuver. JUICE will fire its engines to break into orbit around Ganymede, making it the first spacecraft ever to orbit a moon other than our own. Ganymede is a world of superlatives, and it serves as the primary focus for the latter part of the mission. It is not only the largest moon in the solar system, it is actually larger than the planet Mercury. But its most unique feature is that it is the only moon known to possess its own intrinsic magnetic field, a miniature version of Earth's generated by a liquid iron core. This creates a fascinating and complex interaction with Jupiter's own powerful magnetic field, resulting in a mini magnetosphere nestled within the giant one. JUICE will spend nearly a year orbiting Ganymede, mapping its surface in unprecedented detail, studying the composition of its icy shell, and probing the structure of its internal ocean. A key instrument, a laser altimeter, will measure the moon's tides. Just as the moon's gravity pulls on Earth's oceans, Jupiter's gravity flexes Ganymede. By measuring the subtle bulging of the ice shell, scientists can deduce the thickness of the ice and the depth and salinity of the hidden ocean below. To accomplish its goals, JUICE is equipped with a powerful suite of 10 instruments, each designed to probe a different aspect of the system. A powerful radar system will penetrate the icy crusts of all 3 moons, sending signals deep below the surface to map the interface between the ice and the liquid ocean, potentially revealing variations in shell thickness and locating water bodies closer to the surface. A laser altimeter will create precise topographic maps, while a suite of optical and spectral images will analyze the surface composition, searching for salts and organic molecules that may have welled up from the ocean below. Particularly important are the particles and fields instruments, which will measure the charged particles and plasma environment around the moons. This will help scientists understand how Jupiter's fierce radiation belt affects the moon's surfaces, and crucially, how energy and material might be transferred from the moons back into the Jovian system, a process that could provide chemical energy for life in the dark oceans. The ultimate quest for JUICE is to assess the habitability of these subsurface oceans. It will not directly detect life, but it will gather all the evidence needed to determine if these alien seas possess the necessary conditions. The mission will look for 3 key ingredients: liquid water, chemical building blocks, and a source of energy. The presence of water is almost certain, but JUICE will help determine its nature. Is it a global ocean or a layered series of seas? Is it in contact with a rocky seafloor, which would allow for the leaching of minerals and nutrients essential for life? The detection of specific organic molecules on the surface would indicate that the basic chemistry for life is present. And by studying the complex gravitational and magnetic interactions between the moons and Jupiter, the mission will assess whether tidal heating, the friction generated by the gravitational tug of war, provides enough thermal energy to power hydrothermal vents on the ocean floor, analogous to the life-sustaining ecosystems found in Earth's deep oceans. By comparing Ganymede, Callisto, and Europa, JUICE will paint a complete picture of how these ocean worlds evolve. Europa is young and active, its surface constantly renewed, suggesting a strong connection between its ocean and the surface. Callisto appears ancient and inert, a fossil world that may have a quieter, more isolated ocean. Ganymede sits in the middle with a complex geological history and its own magnetic field. Understanding the differences between these three siblings will tell us about the diversity of habitable environments and the likelihood of life arising in such dark, distant seas. The data from JUICE, combined with the focused findings from Europa Clipper, will provide humanity with our first comprehensive understanding of this miniature solar system within our own, revealing whether the most common abodes for life in the universe are not planets like Earth, but the hidden oceans of icy moons. While observatories like the James Webb and Roman space telescopes focus intensely on specific cosmic questions, sometimes the most profound discoveries come not from a deep gaze at a single target, but from an impossibly wide view of the entire cosmos. This is the ambitious goal of NASA's SPHEREX mission, a unique surveyor that will create a revolutionary new map of the sky, not as a static picture, but as a three-dimensional cosmic atlas. Unlike any mission before it, SPHEREX will scan the entire sky not just once, but multiple times, observing hundreds of millions of galaxies and stars in over 90 different colors of infrared light. Its name, the spectrophotometer for the history of the universe, epoch of reionization and ICE's explorer, reveals its extraordinary dual mission: to answer questions about the very largest structures in the universe and the very smallest building blocks of life, all within a single, sweeping survey. The first of its grand ambitions is to investigate the universe's infancy, specifically a pivotal era known as the epoch of reionization. This was a cosmic turning point that occurred several hundred million years after the Big Bang, when the first stars and galaxies switched on, flooding the universe with its first light. This intense ultraviolet radiation began to rip apart or reionize the neutral hydrogen gas that filled the cosmos, fundamentally changing its nature. SPHEREX will study this era by mapping the three-dimensional positions of millions of galaxies across vast cosmic distances. It will achieve this not by taking pretty pictures, but by capturing the spectrum of every single object it sees. By measuring how much the light from these distant galaxies has been stretched or redshifted by the expansion of the universe, the mission can calculate their distance from Earth. Over its 2-year planned survey, it will assemble a three-dimensional map of the universe on a scale never before attempted, revealing the large-scale structure of cosmic matter. This three-dimensional map is key to unlocking the secrets of the universe's expansion. Within this vast cosmic web of galaxies, SPHEREX will look for a faint, repeating pattern known as baryon acoustic oscillations. Imagine the early universe as a hot, dense soup of particles and light. Pressure waves, much like sound waves, rippled through this primordial plasma. When the universe cooled enough for atoms to form, these waves froze in place, leaving a faint imprint, a preferred distance between galaxies. This cosmic ruler is imprinted on the distribution of galaxies across the universe. By measuring this standard ruler at different cosmic epochs, SPHEREX will trace how the expansion rate of the universe has changed over billions of years, providing crucial independent data to help us understand the mysterious nature of dark energy. It will determine if dark energy has remained constant, as Einstein's cosmological constant suggests, or if its influence has evolved over time, which would point toward new, undiscovered physics. Simultaneously, SphereX will turn its gaze inward toward our own Milky Way galaxy to investigate the origin of the ingredients for life. As stars are born within dense, cold clouds of gas and dust, these stellar nurseries are also cosmic chemistry labs. On the surfaces of tiny dust grains in these frigid regions, simple atoms and molecules freeze solid, forming layers of ice. Over time, radiation from nearby stars can trigger chemical reactions within these ices, creating more complex organic molecules, the very precursors to the building blocks of life. SphereX is uniquely equipped to be a cosmic ice hunter. Water ice, along with ices of frozen carbon dioxide, carbon monoxide, and methanol, absorb specific wavelengths of infrared light. By taking the spectrum of the light from hundreds of newly forming stars as it filters through these surrounding clouds, SphereX can identify the unique fingerprints of these different ices. The mission will conduct a comprehensive census of these ices in star-forming regions throughout our galaxy. It will measure not just which molecules are present, but also their abundance and how they relate to each other. For instance, does the presence of water ice correlate with the formation of more complex organic molecules? Are certain combinations of ices more common around stars that are forming planetary systems? By surveying a vast number of stellar nurseries, SphereX will help astronomers understand the fundamental processes that seed young planetary systems with water and organic materials. This data will tell us if the delivery of water to planets like Earth is a common outcome of star formation or a rare occurrence. In essence, SphereX will trace the cosmic pathway of water, from its formation on dust grains in cold clouds to its potential incorporation into planets orbiting newborn stars, providing a critical piece of the puzzle in understanding how habitable worlds are built. This mission beautifully bridges the gap between cosmology and astrobiology, using the same set of observations to explore the universe's grandest scales and its most intimate chemical beginnings. While we explore the distant mysteries of the cosmos, it's vital to remember that the greatest immediate threat to our civilization may be lurking much closer to home, hiding in the vast darkness of our own solar system. For all our technological advancement, we remain vulnerable to a primordial danger: asteroid impacts. The history of Earth is written with these catastrophic events, from the demise of the dinosaurs to the Tunguska event in 1908, which flattened a remote Siberian forest with the force of a large nuclear bomb. The challenge isn't just the immense energy these objects carry. It's that many of them are incredibly difficult to see until it's almost too late. This is the critical gap that NASA NEO Surveyor mission is designed to fill, a space telescope with one overriding purpose: to protect our planet by finding and tracking the asteroids we haven't yet discovered. The name itself reveals its mission: Near-Earth Object Surveyor. A near-Earth object, or NEO, is any asteroid or comet whose orbit brings it within about 30 million miles of Earth's path around the Sun. Within that group are the potentially hazardous objects, those large enough to cause regional or global damage, and that come close enough to Earth's orbit to warrant concern. The problem is that our current ground-based telescopes have a major blind spot. They primarily search for asteroids by looking for sunlight reflecting off their surfaces. But many asteroids, especially those that spend most of their time closer to the Sun than Earth does, are very dark. They absorb most of the visible light that hits them, making them nearly invisible to optical surveys. It's like trying to find a piece of charcoal against a black sheet of paper. You need a different kind of vision. This is where NEO Surveyor's revolutionary design comes into play. Instead of looking for reflected sunlight, this space-based observatory will detect the heat signature of asteroids using infrared light. Even the darkest asteroid absorbs energy from the Sun, heats up and re-radiates that energy as infrared warmth. Against the cold backdrop of space, these asteroids glow brightly in the infrared spectrum. By operating from a special vantage point called the Sun-Earth Lagrange Point 1, roughly 1,000,000 miles from Earth in the direction of the Sun, a NEO surveyor will have a continuous and unobstructed view of the skies near the Sun. This allows it to search for those elusive asteroids that approach Earth from the daytime side, the direction from which we are currently almost completely blind. The mission's goal is both simple and ambitious: to discover at least 90% of all near-Earth objects larger than 140 meters in diameter within its first decade of operation. An asteroid of that size could unleash energy equivalent to hundreds of megatons of TNT, enough to devastate an entire continent. By finding these objects, precisely calculating their orbits decades or even centuries in advance, we transform a random natural disaster into a manageable risk. Early warning is the single most important factor in planetary defense. If we know an impact is coming years ahead of time, we have options. We could send a mission like NAS, a successful DART experiment, to nudge the asteroid slightly off course, ensuring it misses Earth entirely. Without that early warning, our options dwindle to virtually nothing. A NEO surveyor represents a fundamental shift from reacting to threats to proactively preventing them. It's a mission born from the understanding that our survival as a technological civilization depends on our awareness of our cosmic environment. This isn't about fear, it's about responsibility. By systematically cataloging the population of near-Earth objects, we are not just doing science, we are taking out a collective insurance policy for humanity, ensuring that our future is not left to cosmic chance. It is a quiet, vigilant sentinel dedicated to the most practical of all space goals, keeping our home world safe. Building on the quest to find other Earths, we now arrive at a mission concept that represents the culmination of this scientific dream. The Habitable Worlds Observatory, or HWO, is envisioned as the ultimate tool in the search for life beyond our solar system. It is not a single, finalized design, but rather a powerful guiding concept for NAS, a next great flagship astrophysics telescope, a project that will take the revolutionary work of the James Webb and Roman telescopes to its logical and most profound conclusion. Where its predecessors have laid the groundwork by discovering thousands of exoplanets and analyzing the atmospheres of large, hot worlds, the Habitable Worlds Observatory has one explicit, breathtaking goal: to directly see, photograph, and study planets that are truly Earth-like, orbiting stars like our Sun, and to search within their light for the definitive chemical signatures of life. The monumental challenge facing this endeavor is one of contrast. Imagine trying to see a firefly hovering right next to a brilliant, high-powered searchlight from thousands of miles away. That is the scale of the problem. A star like our Sun is about 10 billion times brighter than an Earth-like planet orbiting it. To have any hope of detecting the faint, pale blue dot of a distant world, the telescope must have a way to suppress the overwhelming glare of the host star with near-perfect precision. This is the core technological hurdle that the Habitable Worlds Observatory is being designed to overcome, primarily through two advanced and complementary concepts: internal coronagraphs and external starshades. An internal coronagraph is a system of complex masks and deformable mirrors built directly inside the telescope. Think of it as a highly sophisticated pair of sunglasses that can actively cancel out starlight with incredible control. When light from a star and its planet enters the telescope, the coronagraph uses a series of components to block the central, intense starlight, while allowing the much fainter light from the planet to pass through to the camera sensors. The deformable mirrors are the key to this process. They can make tiny, precise adjustments to their shape many times per second to correct for the slightest imperfections in the optical system and ensure that the star's light is suppressed to an unprecedented degree. This technology is already being tested on the Nancy Grace Roman Space Telescope. but the Habitable Worlds Observatory would require a coronagraph that is hundreds of times more effective. The alternative, and perhaps even more elegant, solution is the starshade. This is not a part of the telescope itself, but a separate, giant, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of it, positioned precisely to block the light from a target star. The intricate petal-like shape of the starshade is designed to prevent the bending of starlight, known as diffraction, from spilling around the edges and ruining the observation. When the two spacecraft are perfectly aligned, the starshade casts a deep, ultra-dark shadow onto the telescope, allowing it to see the planetary system in stunning clarity without any of the star's glare. This external occulter would enable observations of unparalleled sensitivity, but it requires an extraordinary feat of formation flying, with two spacecraft maintaining their exact positions relative to each other across vast distances in space. Once the starlight is suppressed, the real science begins. The Habitable Worlds Observatory would not just take a simple picture, it would capture the spectrum of the planet's light. This spectrum is the treasure. By spreading the planet's light out into its constituent colors, scientists can read it like a chemical barcode. They will search for the key atmospheric gases that, when found together, strongly suggest the presence of life. The most promising combination is often called the red edge of vegetation, but more fundamentally, it involves looking for gases that are in chemical disequilibrium. On Earth, our atmosphere contains large amounts of oxygen, which is highly reactive and would quickly disappear if it weren't continuously replenished by photosynthesis. Similarly, the presence of methane, which is rapidly broken down by chemical reactions, suggests an ongoing source. Finding both oxygen and methane in the atmosphere of a distant world would be a powerful, though not definitive, biosignature. The observatory's mission would be one of careful, systematic investigation. It would survey dozens of the nearest sun-like stars, looking for planets residing in their habitable zones, the region where temperatures are just right for liquid water to exist on the surface. For each candidate it finds, it would spend days or weeks gathering enough light to build a high-quality spectrum. This data would tell us not just about potential biosignatures, but about the planet's overall environment. Is there water vapor in the atmosphere? What is the surface pressure? Are there clouds? Could the planet be a runaway greenhouse like Venus, or a frozen wasteland like Mars? The Habitable Worlds Observatory would provide the first truly comprehensive assessment of another Earth's climate and habitability. This mission represents a fundamental leap in our quest to understand our place in the universe. It moves us from the realm of statistical probability and indirect detection into the age of direct characterization. The data it returns would address one of humanity's oldest and most profound questions. Is life a cosmic imperative, a natural outcome of cosmic evolution, or is Earth a singular miracle? The discovery of even a single biosignature on a distant world would suggest that the universe is teeming with life, that biology is as much a part of the cosmos as gravity and light. The Habitable Worlds Observatory is more than a telescope. It is an instrument of philosophical and scientific transformation, designed to give us our first real glimpse of a living world beyond our own, forever changing our perspective on what it means to be alive in the cosmos. But while observatories like the Habitable Worlds Observatory will allow us to gaze at distant Earths from the safety of our solar system, there is a bolder, more radical vision that seeks to do the unthinkable, physically cross the interstellar void. This is the goal of Mission 20 Breakthrough Starshot, an initiative that pushes the boundaries of ambition from the plausible to the truly science-fictional. Conceived as a $100 million research and engineering program, Starshot's objective is almost incomprehensibly daring: to send a fleet of tiny, gram-scale spacecraft to our nearest stellar neighbor, the Alpha Centauri system, and have them complete the journey within a single human lifetime. For context, our current most distant spacecraft, Voyager 1, would take over 70,000 years to reach Alpha Centauri using conventional chemical propulsion. Starshot aims to shrink that timeline to just 20 years, a feat that requires rethinking the very fundamentals of space travel. The core of this revolutionary idea is a dramatic shift in scale and propulsion. Instead of a single, heavy, and complex spacecraft, Starshot envisions a starship, a wafer-thin probe weighing little more than a gram. This nanocraft would contain all the essential miniaturized systems: cameras, photon thrusters, power supplies, and communication equipment, all etched onto a single tiny chip, not much larger than a postage stamp. This minimalist design is crucial because the propulsion method isn't carried on board. The tiny craft would be attached to a light sail, an enormous, ultra-thin, and highly reflective sheet perhaps only a few atoms thick, designed to be as light as possible. The sail itself is the key to the entire concept, acting as a celestial sailboat, but one that is pushed not by wind but by light. This is where the plan moves from innovative to revolutionary. The starship and its sail would be placed in a high Earth orbit. On the ground, an immense array of powerful lasers, spanning perhaps a square kilometer, would then fire in perfect unison, directing a concentrated beam of light energy toward the sail. Unlike sunlight, which provides a very gentle, continuous push, this terrestrial laser array would deliver a colossal burst of power, a photon blast of unprecedented intensity. For a few minutes, the sail would be subjected to a force equivalent to millions of times the power of sunlight, accelerating the tiny probe at a mind-boggling rate. The goal is to achieve a velocity of 20% the speed of light, or about 134 million miles per hour. At that incredible speed, the voyage to Alpha Centauri, a distance of 4.37 light-years, becomes a journey measurable in decades, not millennia. The engineering challenges involved in making this a reality are, without exaggeration, monumental. Every component of the system pushes the limits of current technology. The laser array itself would need to be the most powerful ever built, operating with a combined power of up to 100 gigawatts, all while maintaining a perfectly coherent beam that can stay focused on a sail the size of a picnic table as it recedes into the depths of space. Any tiny imperfection in the sail's surface, any minuscule tear, would cause it to be instantly vaporized by the intense laser energy. The starship, for its part, must be a marvel of miniaturization, packing sophisticated instruments into a gram-scale package that can survive a 20-year journey through the unforgiving environment of interstellar space, including bombardment by cosmic dust grains that, at 20% light speed, would hit with the energy of a nuclear particle. Then comes the problem of communication. How does a 1-gram probe located over 4 light-years away possibly send data back to Earth? The solution is as elegant as it is challenging. The starship would use a tiny, onboard laser powered by a miniature nuclear battery to beam its precious data back to our solar system. The signal, however, would be incredibly faint by the time it reached us, requiring a network of enormous telescopes on Earth, perhaps using the entire diameter of a large crater or a distributed array of receivers, to act as a collective antenna sensitive enough to detect the whisper from the stars. Even a simple photograph of a planet in the Alpha Centauri system would take weeks to transmit bit by bit. The profound implications of a successful Starshot mission, however, justify the staggering difficulty. For the first time, humanity would have a physical presence in another star system. The primary scientific goal would be to fly past Proxima Centauri b, an Earth-sized planet orbiting within the habitable zone of the system's red dwarf star. The tiny probes would scream through the system at relativistic speeds, but in their fleeting passage, their cameras could capture images of this alien world, resolving surface features, analyzing its atmosphere by studying the starlight filtering through it, and determining if it has oceans or clouds. This would not be a blurry pixel from a distant telescope. It would be a family portrait of another Earth taken from its cosmic neighborhood. Breakthrough Starshot is less a fully funded mission and more a long-term research and development program, a beacon guiding the development of transformative technologies. It challenges scientists and engineers to solve problems that today seem insurmountable, driving innovation in photonics, material science, and miniaturization. Success is not guaranteed within our generation or even the next, but the very act of pursuing such a vision reframes our relationship with the cosmos. It asserts that the gulf between stars is not an impassable barrier but a future highway. It transforms our descendants from passive observers of the night sky into an interstellar species, capable of reaching out and touching the stars themselves, one tiny, light-sail-driven chip at a time. While the grand visions of interstellar travel capture the imagination, the practical work of establishing a permanent presence on the Moon is already underway, led not by a single government flag but by a fleet of commercial pioneers. This new chapter in lunar exploration is defined by NASA, a commercial lunar payload services program, and its first operational missions are turning the Moon from a destination into a workplace. The initial voyages of Astrobotic's Peregrine lander and intuitive machines Nova-C represent the crucial first steps in this ambitious endeavor, demonstrating the viability of a commercial delivery service to our celestial neighbor and beginning the essential task of understanding the lunar environment in detail. Astrobotic's Peregrine Mission 1 was a pathfinder in the truest sense, carrying the hopes of a new commercial model along with its scientific payload. The lander itself was designed as a versatile spacecraft, capable of delivering a diverse suite of instruments to the lunar surface. Its primary scientific focus was on the Moon's delicate and poorly understood exosphere, an extremely thin layer of gases clinging to the surface, so tenuous that the molecules within it rarely collide. Understanding this exosphere is vital because it acts as a historical record, preserving traces of materials delivered by comets, solar wind, and even outgassing from the lunar interior. Peregrine carried instruments like the neutron spectrometer system, designed to measure the amount of hydrogen present in the regolith, a key indicator of water ice, and the linear energy transfer spectrometer, which would have provided critical data on the lunar radiation environment, information indispensable for planning the long-term stays of future astronauts. While the mission encountered propulsion challenges that prevented a soft landing, its launch and operation in space marked a significant milestone, proving that commercial landers could successfully navigate the journey to the Moon and opening the door for the missions that followed. That door was kicked wide open by the stunning success of Intuitive Machines' first Nova-C lander, named Odysseus. This mission didn't just reach the Moon, it achieved a precision landing near the lunar South Pole, a region of immense strategic importance due to its suspected reservoirs of water ice in permanently shadowed craters. The technological heart of the Nova-C lander was its autonomous navigation system. Unlike the vast, flat landing sites chosen during the Apollo era, the rugged polar terrain required a spacecraft that could think for itself. As Odysseus descended, its onboard cameras and lasers scanned the surface in real time, comparing the topography against pre-loaded maps to identify and avoid hazardous boulders and slopes, ultimately touching down with an accuracy that previous missions could only dream of. This capability is not a mere improvement. It is a fundamental enabler for the future, allowing us to target specific, resource-rich areas rather than being limited to large, safe, but scientifically less interesting zones. Once on the surface, the lander, affectionately nicknamed ODI, became a platform for a suite of technology demonstrations with profound implications. Among the most critical was the navigation Doppler LiDAR, a sensor that provided extremely precise velocity and range data during the descent, validating a technology that will become standard for all future precision landings. Another experiment, the stereo cameras for lunar plume surface studies, captured high-resolution imagery of the lander's engine plume interacting with the lunar surface. This data is gold for engineers, helping them model how repeated landings in the same area might kick up abrasive dust that could damage surrounding infrastructure, a problem that must be solved before we can build a sustainable lunar base. Perhaps most evocatively, the mission carried a small art project, a testament to the cultural shift toward a more accessible and inclusive lunar future. The success of Intuitive Machine's first mission, followed closely by a second Nova Sea lander aiming for the mountainous and scientifically tantalizing Malapata crater, has irrevocably changed the landscape of lunar exploration. These missions have demonstrated that the CLPS model works. Companies can design, build, and operate landers that deliver NASA, science and technology payloads reliably and cost-effectively. This is not just about saving money, it's about increasing the tempo of exploration. Instead of waiting a decade for a single, multi-billion-dollar government-led mission, we can now expect a regular cadence of lunar deliveries, each one building on the knowledge of the last. These commercial landers are the supply trains, the scouts, and the construction surveyors for the Artemis Program, turning the vision of a sustained lunar presence from a PowerPoint slide into an active, ongoing project. They are proving that the moon is open for business and that the next great leap for humanity will be built on a foundation of commercial ingenuity. Following the spectacular success of NASA's DART mission, which proved we could intentionally deflect an asteroid by crashing a spacecraft into it, a critical new phase of the experiment is about to begin. The act of deflection was the dramatic climax, but to truly turn this concept into a reliable planetary defense technique, we need to understand the full consequences of that impact. Think of it like this: if you push a car, you can see it move, but to predict exactly how another car will respond to a similar push, you need to know its weight, what it's made of, and how the push altered its surface. This is the vital role of the European Space Agency's Hera mission, a spacecraft designed to be the ultimate detective, arriving at the scene of the cosmic collision to gather the forensic evidence that will make planetary defense a precise science. Hera's journey will take it to the same binary asteroid system visited by DART, Didymos, a larger asteroid about 780 meters across, and its smaller moonlet Dimorphos, which is roughly 160 meters in size, the one that was struck. While DART mission was a high-speed, single-act encounter, Hera is a meticulous, long-term investigation. After its launch, it will cruise through space for several years, arriving at the Didymos system in late 2026. Once there, it will not simply fly by. It will slide into a stable orbit around the pair, becoming a permanent artificial moon of these two natural asteroids. From this privileged vantage point, Hera will conduct a detailed survey over several months, using a suite of sophisticated instruments to measure every conceivable property of Dimorphos, the asteroid that was forever changed by the impact. The first and perhaps most crucial measurement Hera will make is the precise mass of Dimorphos. This is a fundamental piece of data that DART could not provide. We know how much momentum DART transferred to the asteroid because we know the spacecraft's mass and velocity. By precisely measuring how much Dimorphos' orbit around Didymos was altered, which telescopes on Earth have already done, we can calculate the change in momentum. But to understand the efficiency of the impact, we need to know the mass of the target. A push will move a light object much more than a heavy one. Hera will determine this mass with extreme accuracy using a clever technique. As the spacecraft orbits the binary system, the gravitational pull of the two asteroids will cause tiny deviations in Hera's path. By meticulously tracking the spacecraft's radio signals, scientists can detect these minuscule tugs and from them calculate the exact masses of both Didymos and Dimorphos. This will finally allow us to calculate the momentum transfer from the impact with precision, a number known as beta, which is the key to scaling this technique for future asteroid threats. But Hera's investigation goes far deeper than a simple way in. It will also conduct a detailed analysis of Dimorphos's composition and internal structure. Was the asteroid a solid chunk of rock or a loose collection of rubble barely held together by gravity, what scientists call a rubble pile? The answer dramatically affects how an impactor like DART works. A solid rock might crater or fragment, while a rubble pile might absorb the impact like a cosmic beanbag, redistributing the energy in a different way. To find out, Hera carries a powerful laser altimeter that will fire millions of laser pulses at the surface, creating a detailed three-dimensional model of Dimorphos's shape and topography. More importantly, it will be accompanied by two tiny CubeSats that will perform their own daring reconnaissance. The first, named Juventus, will make a slow, low-altitude descent, using a radar instrument to peer beneath the surface and map the asteroid's internal structure, revealing whether it is monolithic or a porous pile of boulders and dust. The second CubeSat, named Milani, will focus on the asteroid's composition. It will use a hyperspectral imager to analyze the sunlight reflected off the surface, identifying the specific minerals that make up Dimorphos. This is crucial because the physical properties of the material, whether it's strong like iron nickel or weak like carbonaceous rock, affect how it responds to an impact. Milani will also attempt an even more audacious feat. It will descend close to the surface and potentially kick up a small cloud of dust, which its instruments will then analyze to determine the exact chemical makeup of the asteroid. Together, these three spacecraft, the Hera mothership and its two CubeSat scouts, will provide a holistic picture of Dimorphos that is unparalleled for any asteroid we have visited. The crown jewel of Hera's investigation will be the close-up study of the crater left by DART. No one knows exactly what this scar will look like. The crater could be relatively small and neat, or it could be massive and irregular, perhaps even having reshaped the entire asteroid. Hera's high-resolution cameras will beam back images of the impact site, allowing scientists to measure the crater's exact size and morphology. This will reveal how the asteroid's material behaved during the hypervelocity collision. Did it act like hard rock shattering or like soft sand flowing? The volume of material ejected from the crater is also a critical factor, as the recoil from that ejected debris plume contributed significantly to the overall push that Dimorphos received, like a jet of gas pushing a balloon. By characterizing the crater, Hera will complete the physics experiment that DART began, turning a single successful demonstration into a validated and predictable model that can be used to design future deflection missions for any asteroid we might find on a dangerous path. This European mission ensures that the pioneering blow struck by DART is not an isolated event, but the foundational step in a robust global planetary defense strategy. And now, our attention turns from the deliberate deflection of one asteroid to the extraordinarily close flyby of another, an event that will transform a celestial object from a subject of concern into a world-class scientific opportunity. This brings us to the remarkable extended mission of NASA OSIRIS-REx spacecraft, now renamed OSIRIS-APEX. You may remember this mission for its incredible success in collecting a sample from the asteroid Bennu, a precious cargo now safely on Earth. But rather than retiring, this veteran spacecraft is embarking on a second act, a daring voyage to rendezvous with one of the most famous near-Earth asteroids, Apophis. The mission's timing is perfectly synchronized with a rare cosmic event, allowing it to study an asteroid in a unique state of change, revealing secrets that are usually locked away deep inside these ancient bodies. The focus of this new chapter, Apophis, gained notoriety shortly after its discovery in 2004, when initial orbital calculations suggested a small but unsettling probability of an impact with Earth in the year 2029. While more precise observations quickly ruled out any impact risk for at least the next century, the asteroid's upcoming approach on April 13, 2029 remains historic. On that day, Apophis will come breathtakingly close to Earth, passing within just 32,000 kilometers of our planet's surface. That is closer than some of our geostationary weather and communication satellites. While there is absolutely no danger of a collision, the asteroid's proximity will be a spectacular event, visible to the naked eye in the eastern hemisphere. But for scientists, the true spectacle begins just after the flyby, and that is precisely when Osiris Apex will arrive. The immense gravitational pull of Earth during this close pass will act as a natural laboratory, performing an experiment on Apophis that we could never replicate. The planet's gravity will significantly perturb the asteroid, altering its orbit, its rotation rate, and potentially even its shape. It is this very perturbation that makes the mission so scientifically valuable. Think of it like shaking a box to figure out what is inside without opening it. The way Apophis responds to this gravitational shake will tell us volumes about its internal structure. Is it a single, solid chunk of rock or a loose collection of boulders and dust, a rubble pile held together by its own minuscule gravity? A solid body would respond to the flyby with a subtle, unified change. A rubble pile, however, might wobble, shift, or even experience landslides on its surface as the individual components readjust to the new forces acting upon them. Osiris Apex will be there to document every change. The spacecraft's arrival at Apophis is scheduled for 2029, shortly after the Earth flyby. It will then commence an 18-month investigation, using the same suite of sophisticated instruments that proved so successful at Bennu. Its cameras will map the entire surface in high resolution, searching for any new fractures, dust avalanches, or shifts in boulder fields caused by the Earth's gravity. Its spectrometers will analyze the composition of the surface, looking for any freshly exposed material that was previously buried. But the mission will go even further. In a bold maneuver reminiscent of its sample collection at Bennu, Osiris Apex will not just observe from a distance, it will get intimately close. The spacecraft will dip down toward the surface and fire its thrusters, kicking up rocks and dust. This deliberate disturbance serves a critical purpose: to expose the subsurface layer, allowing scientists to study material that hasn't been altered by billions of years of exposure to the harsh space environment, and to analyze the physical properties of the regolith in situ. By comparing the pre-flyby and post-flyby state of Apophis, the Osiris Apex mission will achieve a breakthrough in our understanding of asteroid dynamics and composition. The data will refine our models of how gravitational interactions can reshape these small bodies, which is essential for accurately predicting the long-term orbits of other near-Earth objects. Furthermore, understanding whether an asteroid like Apophis is monolithic or a rubble pile is the single most important factor in designing a future planetary defense mission. Deflecting a solid rock requires a different strategy than nudging a fragile collection of boulders. This extended mission transforms a spacecraft that has already made history into a vital tool for both pure science and planetary security, ensuring that its journey of discovery continues to yield profound insights into the building blocks of our solar system and the forces that shape their path. While the commercial landers are scouting potential outpost sites, NASA is preparing to send its own dedicated prospector to the lunar South Pole, a robotic geologist designed for one critical task: finding the water. This is the Volatiles Investigating Polar Exploration Rover, or VIPER, a mission that represents the next logical step in the Artemis Program's goal of sustainable exploration. VIPER is not just another lander, it is NASA's first robotic moon rover since the days of Apollo, and its mission is both straightforward and revolutionary. It will embark on a 100-day journey across the rugged, shadowed terrain near the Nobile crater, armed with a sophisticated drill and a suite of instruments with a single objective: to create the first ever global resource map of the moon, pinpointing exactly where the water ice is, how much of it exists, and in what form it can be found. The challenge of operating at the lunar poles is unlike any other environment we have explored. Unlike the equatorial regions visited by Apollo, which experience consistent 2-week-long days and nights, the poles are a land of eternal low angles and extreme contrast. Some mountain peaks are bathed in near-perpetual sunlight, ideal for generating solar power, while deep, neighboring craters have not seen a single ray of sunlight for billions of years, creating some of the coldest places in the entire solar system. It is within these permanently shadowed regions that water ice, delivered by comets and asteroids over eons, has likely been preserved in a deep freeze. Viper is specifically engineered to navigate this challenging landscape. It is a sizable rover about the size of a golf cart, and its key to survival is its ability to live off the land in terms of power. It is equipped with a large solar panel that can tilt and angle itself to maximize energy capture from the sun, which always hangs low on the horizon at the pole. Crucially, Viper must also be able to drive directly into these bitterly cold, permanently shadowed craters, operating on battery power for up to 50 hours at a time before needing to retreat to a sunlit area to recharge. The heart of Viper's scientific capability is its 1-meter-long drill, known as the regolith and ice drill for exploring new terrain, or trident. This is not a simple scoop. It is a rotary percussive drill capable of chewing through the tough, compacted lunar soil and extracting samples from up to a meter below the surface. This depth is critical because water ice is not expected to be stable on the very surface. It would sublimate or turn directly from a solid into a gas when exposed to the vacuum of space. Instead, scientists believe the ice is mixed with the soil or regolith, forming a layer beneath a protective dry topsoil. Viper will use its drill to collect samples from at least 3 different locations with varying temperatures and sun exposure. Inside the frigid, permanent shadows, on the line between light and shadow where conditions change drastically, and in areas that are mostly sunlit. By comparing the water content in these different environments, the rover will answer fundamental questions about how the ice arrived on the Moon and how it is preserved. Once a sample is drilled, Viper will not send it back to Earth. Instead, it will perform the analysis right there on the spot using its onboard laboratory. The rover carries 3 specialized instruments to analyze the samples. The mass spectrometer observing lunar operations, or MSOLO, will sniff the gases that are released as the drilled soil warms up inside the rover, identifying the specific chemical compounds present. The near-infrared volatile spectrometer system, or NIRVs, will shine light on the sample to determine its composition, looking for the unmistakable spectral signature of water ice and other volatile compounds like carbon dioxide and methane. A 4th instrument, the neutron spectrometer system, will act as a scout, looking a meter or so ahead of the rover to detect the presence of hydrogen, a proxy for water in the subsurface. This allows the team to decide where to drill next, making Viper mission an intelligent, adaptive search. The data Viper returns will be the foundation for every future decision about a sustained human presence on the Moon. Knowing the concentration of water ice is the difference between a feasible plan and a fantasy. If the ice is plentiful and relatively pure, it could be mined and processed with straightforward mechanical equipment. If it is sparse and mixed deeply with soil, more complex extraction methods would be required. This information will directly influence the design of the processing plants that will one day turn lunar ice into breathable air and rocket fuel. It will determine the exact location of the Artemis base camp, placing it as close as possible to this invaluable resource. Viper is therefore much more than a science mission. It is the critical first survey for a lunar economy, transforming the promise of celestial resources into a tangible, mapped, and quantified reality, ensuring that when astronauts return, they will know exactly where to dig. The incredible observatories of today, like the James Webb and Roman telescopes, are already reshaping our understanding of the cosmos, but the architects of astronomy are not resting. They are already designing the next generation of eyes on the sky, machines that will peer even deeper into the universe's secrets and directly image Earth like worlds around other stars. The ambition driving these concepts is to answer the most profound questions we can pose. How did the first stars and galaxies truly ignite? Are we alone in the universe? And what is the ultimate fate of everything? One of the most exciting and mature concepts on the drawing board is the Habitable Worlds Observatory, or HWO. Envisioned as NASA's next flagship astrophysics mission, the HWO is not merely an incremental improvement. It is a technological leap with a singular, breathtaking goal. Its primary objective is to directly image and analyze the atmospheres of at least 25 potentially Earth-like planets orbiting Sun-like stars. To accomplish this, it must solve the ultimate challenge in astronomy, separating the incredibly faint light of a pale blue dot from the overwhelming glare of its host star, a contrast ratio of 10 billion to 1. The leading designs to achieve this almost miraculous feat involve either a sophisticated internal coronagraph, a system of complex masks and deformable mirrors within the telescope itself, or a separate flower-shaped spacecraft called a starshade that would fly tens of thousands of kilometers ahead, perfectly positioned to block the starlight and cast a deep shadow for the telescope to observe. Within, by capturing the spectrum of light from these distant worlds, the HWO will search for the chemical fingerprints of life, not just oxygen or methane alone, but combinations of gases that are in chemical disequilibrium, suggesting an ongoing biological process. This mission would move us from statistical probability to direct characterization, potentially providing the first convincing evidence that biology is not unique to Earth. Looking even further ahead, astronomers are contemplating telescopes of a scale that dwarfs today's observatories. One visionary idea involves constructing an interferometer in space. Instead of a single large mirror, an interferometer would use a fleet of smaller telescope mirrors flying in precise formation, separated by vast distances. By combining their light, they can simulate the resolving power of a single mirror as wide as the distance between them. A space-based interferometer with components spread across hundreds of kilometers could achieve an angular resolution so sharp it could, in theory, map the surfaces of exoplanets or observe the event horizons of black holes in distant galaxies in stunning detail. The engineering challenges are immense, requiring nanometer-level precision in maintaining the formation of spacecraft flying millions of kilometers from Earth. But the scientific payoff would be a revolutionary new window into the physics of the most extreme objects in the universe. Perhaps the most profound goal for a future observatory is to gaze back to a time before the first stars, a period cosmologists call the cosmic dark ages. After the Big Bang, the universe was a hot, opaque plasma. As it expanded and cooled, it eventually became neutral and transparent, but it was utterly dark, devoid of any light sources. This era lasted for hundreds of millions of years, until gravity pulled together the first clumps of hydrogen and helium gas, igniting the very first stars. To witness this cosmic dawn, we need a telescope that can see in ultra-long wavelength radio waves, specifically the signal from neutral hydrogen, at a time when its light has been redshifted by the expansion of the universe into the meta wave band. A proposed telescope on the far side of the Moon could be ideal for this task. The lunar far side is permanently shielded from the radio noise of Earth, offering the quietest location in the inner solar system. A large array of simple radio antennas deployed there could, for the first time, detect the faint whisper of that primordial hydrogen, creating a map of the universe as it was before the first dawn. This would allow us to watch the large-scale structures of the cosmos literally turn on, revealing how the first galaxies assembled from the featureless dark. Each of these future observatories requires technological leaps that sound like science fiction. Building the HWO demands advancements in ultra-stable optics and active wavefront control systems far beyond what we have today. A large space interferometer hinges on breakthroughs in autonomous formation, flying, and laser communication. A Dark Ages telescope requires deploying a vast array of instruments on the moon robotically. Yet the pursuit of these technologies consistently spurs innovation that finds applications far beyond astronomy. The quest to answer our deepest questions about the universe continues to push the boundaries of the possible, ensuring that the golden age of discovery is not a moment in time, but a continuous journey into the unknown. But for humanity to truly thrive beyond Earth, we need more than just rockets and rovers. We need a reliable way to stay connected, to share information across the void with the same ease we experience on our home planet. This brings us to a critical yet often overlooked piece of the spacefaring puzzle: the interplanetary internet. The communication networks we rely on today, built on protocols like the Internet Protocol or IP that powers the World Wide Web, simply cannot function across the immense distances and time delays of space. Sending a signal to Mars, for instance, can take anywhere from 4 to 24 minutes for a simple round trip, depending on the planet's positions in their orbits. A system that requires constant, instantaneous handshakes and acknowledgements would collapse under such lag. So, a completely new architecture is required, one designed for patience and resilience in an environment where data must often be stored and forwarded across a celestial relay race. This is the purpose of the Delay/Disruption Tolerant Networking Protocol, or DTN. Think of DTN not as a replacement for the Internet, but as an interplanetary postal service. On Earth, when you send an email, the system expects an immediate confirmation of receipt. In space, that's impossible. DTN solves this by operating on a store and forward principle. Each node in the network, which could be a satellite orbiting the Moon, a relay orbiter at Mars, or a deep space gateway, acts as a digital post office. It receives a bundle of data, stores it securely, and then holds onto it until the next link in the chain, perhaps another spacecraft, comes within range. Once a connection is established, the data bundle is forwarded onto the next node, gradually hopping its way across the solar system until it reaches its final destination. This method ensures that no data is lost, even if a critical link is temporarily unavailable because a planet has rotated or a spacecraft is on the far side of the Sun. To dramatically increase the amount of data we can send through this interplanetary postal system, engineers are turning from radio waves to a much more powerful medium, light. Laser communications or optical communications represent a quantum leap in space connectivity. The principle is similar to using fiber optics, but without the fiber, it's a wireless beam of light carrying encoded information. The advantage is immense bandwidth. Just as a single optical fiber can carry vastly more data than a copper wire, a laser beam can transmit information at rates 10 to 100 times faster than the best radio systems. This means that a high-resolution map of an entire Martian region that might take weeks to download via radio could be transmitted in a matter of days or even hours. It would allow future astronauts on Mars to stream high-definition video from the surface, or for a complex rover to send back a torrent of scientific data, transforming our ability to explore remotely. NASA's recent demonstrations have proven this technology is not just a theory. The Psyche mission, on its way to the metallic asteroid, is testing a system called Deep Space Optical Communications, or DSOC. It successfully beamed a near-infrared laser encoded with test data from far beyond the Moon's orbit to a telescope in California, achieving record-breaking data rates. Closer to home, the lunar laser communication demonstration on the LADEE orbiter showed that gigabit-per-second speeds are possible between the Moon and Earth. The challenge, of course, is the need for incredible precision. Aiming a laser beam across millions of kilometers is like hitting a moving dime from 1,000 miles away. It requires ultra-stable telescopes and sophisticated pointing systems on both the transmitter and the receiver. But as these technologies mature, they will form the high-speed backbone of the solar system internet, with DTN providing the robust routing protocol that ensures the data gets where it needs to go, no matter the delay. The ultimate vision is a fully integrated solar system-wide network. Imagine a future where constellations of satellites around Mars, known as the Mars Satellite Network, provide constant coverage of the entire planet, just like GPS and communication satellites do on Earth. Rovers, landers, and astronauts on the surface would have continuous high-bandwidth connections to orbiting relays, which would then use powerful laser links to send the data back to Earth. A similar system, Lunar Net, is already being planned for the Moon. This infrastructure would make operating on another world feel far more familiar. An astronaut in a Martian habitat could consult with experts on Earth in near real time, reviewing complex geological data together. A malfunctioning rover could have its software patched remotely. The immense volumes of data from telescopes positioned in the quiet zones far from Earth could be streamed back effortlessly. This interplanetary internet is the silent, invisible framework that will bind our future settlements together, turning isolated outposts into a truly connected multi-planet civilization. For decades, the International Space Station has stood as a singular symbol of human cooperation and orbital presence, an unparalleled laboratory in the sky. But its time, while immensely productive, is finite. The plan now is for a deliberate and historic transition, shifting the center of gravity in low Earth orbit from a government-run outpost to a new era of commercially owned and operated space stations. This isn't about abandoning our foothold in space. It's about building a vibrant, sustainable neighborhood there, one driven by the innovation and economic forces of private enterprise. Companies like Axiom Space are at the forefront of this movement, and their strategy for building the future is as ingenious as it is practical. Their plan begins not with a clean slate, but by literally plugging into the existing infrastructure of the ISS itself. Axiom's approach involves constructing a series of their own modules, which will initially dock with the International Space Station. Think of this as adding new rooms to a house before eventually building a whole new, independent home next door. These new modules are not simple copies of the aging ISS components. They are designed with modern technology, greater comfort, and commercial efficiency in mind. They will feature larger windows for observation, more user-friendly interiors, and advanced systems that are easier and cheaper to maintain. During this initial phase, Axiom will use the ISS as a power source and a structural anchor, allowing their customers, which could include national space agencies, private researchers, or even tourists, to live and work aboard their new facilities while still having access to the established laboratory space of the main station. This phased method dramatically reduces risk and provides a steady, proven environment in which to test their systems and build a customer base. The pivotal moment comes when the International Space Station is eventually retired. At that point, these Axiom modules will detach and become the core of a new, free-flying commercial space station, dubbed Axiom Station. This elegantly avoids a situation where the end of the ISS program would mean a gap in the United States' continuous presence in orbit. Instead of a cliff edge, it creates a seamless handoff, ensuring that the invaluable capability for humans to live and work in microgravity continues without interruption. This model also opens the door for other companies, like Blue Origin with its orbital reef concept or Voyager Space's Starlab, to establish their own destinations, fostering a competitive marketplace in space. The implications of this shift are profound, particularly for the democratization of access to space. The high cost and limited availability of resources on the ISS have historically restricted its use primarily to large government agencies and a handful of well-funded academic experiments. A commercial model driven by competition and the need to turn a profit inherently incentivizes companies to find ways to lower costs and increase efficiency. This could make buying a ticket to orbit or renting lab space a realistic prospect for a much wider range of participants: smaller universities, mid-sized corporations, and innovative startups. The types of activities conducted in orbit will explode in diversity. We could see specialized manufacturing of pharmaceuticals or unique materials that can only be produced in microgravity, the development of new alloys, and the large-scale cultivation of tissues for medical research. The unique environment of space offers a purity and control that is impossible to achieve in Earth's gravity, and commercial stations will provide the factory floor to exploit these advantages. This expansion will naturally extend to space tourism, but in a more substantial and integrated way than the brief suborbital flights we've seen. A commercial station could host not just wealthy individuals for short visits, but also offer longer-term stays for citizen astronauts participating in research or artistic endeavors. Imagine a filmmaker producing a documentary entirely in orbit, or an engineer testing a new piece of hardware they designed. The business models will be as varied as the customers, potentially including everything from sponsored research for consumer brands to educational outreach programs that allow students to conduct their own experiments remotely. This commercial ecosystem will do more than just fund the stations. It will weave space into the fabric of our global economy and culture, transforming it from a remote frontier into an accessible domain for human enterprise. The rise of commercial space stations marks the moment we stop just visiting space and truly begin to live and work there as a regular part of human activity. What we have witnessed across these 25 missions is nothing less than a panoramic view of a species awakening to its cosmic potential. From the James Webb Space Telescope peering back to the dawn of time, to the Artemis Program laying the groundwork for a city on the moon, to ventures like Breakthrough Starshot contemplating journeys to the stars themselves, the scope is staggering. We are no longer content to simply gaze up at the silent points of light. We are now actively reaching out, probing, and preparing to stay. These missions, in their incredible diversity, share a common thread of transformative ambition. They aim to answer the oldest philosophical questions about our solitude in the universe, to secure our planet from ancient threats, and to master the skills needed to thrive on other worlds. Each one, from the Martian sample returned to the icy ocean explorers at Jupiter and Saturn, is a piece of a much larger puzzle, a blueprint for a future where humanity is no longer confined to a single planet. Collectively, they signal a fundamental and irreversible shift in our relationship with the cosmos. For all of history, space was a backdrop, a distant realm of mystery and myth. Today, it is becoming a domain of human activity. We are transitioning from being passive observers of the heavens to active participants in a cosmic drama. This is the difference between studying the ocean from the shore and learning to build ships to sail across it. The commercial landers, the plans for a lunar internet, and the development of in-situ resource utilization are not just technical projects. They are the foundational pillars of a spacefaring civilization. They represent a future where the moon is a hub, Mars is a frontier, and the resources of the solar system are within our grasp to use responsibly. This is not a distant dream. It is the direct consequence of the missions we are flying right now. The most inspiring aspect of this new chapter is that it is unfolding in real time, and everyone has a front row seat. The images from new worlds, the data revealing cosmic secrets, the triumphs and even the setbacks of these daring endeavors are stories that belong to all of us. They are a testament to our shared curiosity, our resilience, and our boundless ingenuity. So we encourage you not to see this as an ending, but as an invitation. Follow these missions as they progress, watch the launches, read the discoveries, and share in the wonder, because their successes will not just belong to the scientists and engineers who built them. They will ripple through our culture, our economy, and our understanding of our place in the universe. They have the power to inspire a new generation, to unite humanity in a common, peaceful goal, and ultimately, to change everything we know about what is possible. The next great discovery is already on its way, hurtling through the void, and its story is